Hello and welcome. Today we're going to take a look at how to create a TensorFlow Lite model for our first tech challenge in LAUSD. So for the first tech challenge, our game is going to be consisting of elements that can only be completed if your robot can visually detect specific objects in the field. So for this season in 2022-2023, teams can earn points for detecting cone sleeve images and parking their robot in the corresponding tiles during the autonomous period. If a team creates and trains their robot to detect a custom cone sleeve, they can earn double the points for this task. And you can read more about scoring and this specific autonomous period task in the FTC Game Manual Part 2 if you click this link here. So what is TensorFlow, or TF Lite? So TensorFlow is a free and open source software library for machine learning, or ML, and artificial intelligence, AI. It can be used across a wide range of tasks, but has particular focus on training and inference of deep neural networks. If you want more information about specifically what that means, there's a nice link to the Wikipedia article about TensorFlow. But essentially, we're going to be using this technology to train the software on our robot to look at an image through a webcam and determine what objects are in that image. And we're going to be also doing all of this in this Google Colab document, or notebook as it's known. Colab allows you to do several things, but its main use is to execute Python in your web browser with no installation into your computer, no configuration. It allows your browser access to GPUs, or graphical processing units, which are very powerful, more powerful than your computer's CPU. So we're going to be training our robot with TensorFlow Lite. TensorFlow Lite is a version of TensorFlow that's designed to work on mobile devices or low-powered devices, much like the Rev control hub we use on our robot. Quick note, if for any reason you disconnect from this notebook while completing any one step, you may need to completely restart this process because there are certain variables and things going on in the background that are not saved between Colab sessions. Also note that this method of training TensorFlow Lite models is different than what is prescribed from First Inspires themselves. So First Inspires has their own machine learning tool at ftc-ml.firstinspires.org. However, we do not have access to this tool. So the model we're going to create, the machine learning model we're going to create from this tutorial, because of that, only works with a specifically updated robot controller app for your Rev Control Hub. This app has been updated by myself and allows the model we'll create here to run on your Rev Control Hub. And we'll go over how to install that updated app onto the Control Hub towards the end of this notebook. Now we need to prepare our data set. So it might be helpful to read about TensorFlow on the FTC Docs website before designing your custom cone sleeve. And you need to read the FTC Docs about recording your video and the document about optimizing videos. So for this tutorial, we're going to be training our computer to recognize objects through the use of a video that you create. So now, although the tips you'll read about are about using the ftc-ml, or machine learning tool, these same tips apply to this tutorial as well. It's very helpful to use the same camera your robot will use to record this video, and it's also helpful to reduce the frame rate of that video as well, so that our TensorFlow Lite model can run much faster. Make sure you record all the sleeve images in a single video. This is going to make labeling them much easier and training our model much easier. It's okay to record them all in the same frame of the video if you want, but your robot is never going to see all three of the images at once, so it might actually confuse your robot model. I recommend recording the video in your field, in a location and at a height with a background that it might encounter during an actual competition match. And depending on the frame rate you record your video at, a 20-second video makes around 600 photos out of the frames. And this should be more than enough to train your model. Anything more than that, and it's going to start taking a lot longer to train. So after recording your video, please make sure it's on your computer from whatever device you recorded it on. And then we're going to do something where we create annotations. These are labels that we're going to put on the video you created. And those labels are going to inform our TensorFlow Lite model what object is what. So it can learn, oh, that's the first image on the cone. Oh, that's the second image on the cone, and so on. So to do this, we're going to use a website called cvat.ai. This is a free product. They do have a paid version that is not going to be necessary for what we need to do. And so you're going to go to cvat.ai and click the Try for Free button to get started. You can sign in with any Google account, including your LAUSD Google account, for free. So click the Try for Free button in the top right. So after you sign in, you'll be brought to this page. Please make your way to the tax page. This should be the first page you're brought to after signing in for the first time. You'll note there's no tasks yet. You're going to create one by clicking this plus button and clicking Create a New Task. You'll need to give this task a name. So we can call it Video Annotation, or whatever makes sense to you. We don't need to give it a project name. We're also going to create some labels so that when we're annotating or labeling objects in our video, we have labels to give it. So we'll click the Label Plus button and we'll add the labels we want. So in my video, I had 3 cone sleeve images. So I'm just going to name them Image 1, and I'll click Continue. And then I'll type in another label name, Image 2. And I have 3 images I want to train, so I'll label the third one Image 3. Not very creative names, but that is okay. Don't forget to click Continue there. You'll see what you type disappear into the background. If you want to make sure that that worked properly, if you click on the Raw tab, you'll note that you have those names in there in this strange format. So now we need to connect our video to this. So if you click or drag files into this area, including your video, it will upload to this website. So let me grab my video here that I called ftc-video.mov, and I'll just drag it on. There we are. You can do this for multiple videos or images, but if you have correctly recorded yourself with all 3 cone sleeve images, one video is going to be plenty. We want to kind of limit how many frames and how many different things we need to label, because the more we have, the better the model will be trained, the better it will be at detecting it, but the longer it will take to train. So there's a trade-off for the length of time of our video and how long it takes to train and how accurate it is. And there's diminishing return on that. So if we recorded a video that's like 20 minutes long, it's going to take a very long time to label all the objects in it, and it will take an even longer time to train the model. And it won't be much better than someone who took a video for 20 to 30 seconds. So after we've dragged over our video, we're going to click the Submit and Open button. And it might take a little bit of time to upload your video and get it prepared for the task at hand. Now that your video has been uploaded, you'll be brought to this page. You'll see a still of your video. Now, the video I recorded is not in the field, since I'm doing this at my house. Yours should be, so that your model can be trained to recognize these cone sleeve images properly in the right context. So if you scroll down on this page, you'll note that a job has been created for you. So we're going to click on the link to that job, and you'll note it's in the annotation stage. It's the labeling stage. We're going to tell the computer, okay, this is the object we want our computer to learn how to detect. So once you're on this page, we're going to start labeling or annotating our objects in our video. So to do so, to make this a little easier, they actually have some machine learning technology built into CVAT. And to do that, to get to the what's known as Open Computer Vision or OpenCV tools, is this little icon here underneath the magic wand. You'll notice it says OpenCV. And you're going to click on that tab and go to Tracking. What this is going to allow us to do is label an object and then ask CVAT to try and track it during the playing of the video, so that we don't have to label every single frame to tell the computer what object's what. So we're going to take a look at image number 1 first, which you see is in the first frame of my video here. And we're going to click the track button. After we click that, you'll note some red crosshairs. And we're going to click and drag the object we want to track. And after you create this rectangular box, feel free to edit it slightly. We want to include the entirety of our image, but we also want to keep it very tight and not accidentally include parts that we don't want to label as image number 1. So we've labeled now just a single frame of our about 600 frame video here. And because we've made this trackable, if we click this play button, CVAT is going to try and figure out where that is in subsequent frames. So let's click that play button, or you can click the space bar on your computer to play and then to stop. So let's play. If at any point during this tracking you note the rectangle that's labeling your cone sleeve image is not quite fitting it anymore, feel free to pause the tracking, the playing of the video, and readjust that labeling or annotation rectangle to properly fit. You could even go back to previous frames that you think, oh, you know what, that's not really covering my entire image, or that's placed a little off. So we're going to fix just a few frames there, and then we'll click play again. And whenever CVAT comes to a new frame that it's never looked at before, it's going to continue trying to track that image. You see again, as my image got closer to the camera, the tracking was a little bit off. So I'm going to pause and readjust this annotation, and I'll click play again. And right here you'll note I'm turning the cone to view the next image. So you'll see the tracking is going to still try to figure out where that was. So we need to tell CVAT that that object is no longer there. So you'll note now it's tracking an image that's not there at all. And we're accidentally labeling it as image 1 when these frames do not show image 1. So we're going to go back several frames. You can either click this back button right next to the play button, or press the letter D on your keyboard and it will go back frame at a time. So let's go back to the frames where it started disappearing. So I'm just going to make sure that this rectangle is properly covering just the image and not anything extraneous. There we go. You can go forward in frames by clicking this button next to the play button, or clicking the F key on your keyboard. So I get a little bit too much of the cone there. So as this turns sideways, these are going to need to get thinner and thinner. I don't want to include any of my head in there. when you record your video, it might be good to have as little of yourself in there as possible, as your robot's never going to be looking at a background where there's a person or a hand in the way. So I'd say right about here, we really aren't seeing much, if any, of the actual cone sleeves. So I'm going to say this is going to be my last frame tracking image 1 from my cone. So I'm going to go to the next frame, and you'll note it still has the label here because I had played the video past this, but I don't want this annotation anymore. So if you click on the annotation with the right mouse button, or if you're on a laptop, use 2 fingers to click, you're going to bring up this little menu here. And to disable this annotation for the remainder of the video, or if it comes back later, we could re-enable it. We're going to click the switch outside property, or click the letter O on your keyboard. We're going to say that that object is now outside of the video. And now you'll see the annotation has gone away. Now we do have that on several frames, so let's do that for several of them. And now it's no longer there. And now my next image is there. In fact, it was there a few frames back. Right about here, I can see the full image. So once again, I'm going to go to my Open CV menu on the left-hand side underneath the magic wand and click Tracking. And this time, we're going to track image 2. So I'm going to click the label image 2, click Track, and then make a rectangle around the item I would like to track. Once again, as I press play or move forward through the frames, it's going to try and label what I have in that rectangle as much as it possibly can. And if at any point I realize it's not quite tracking it perfectly, or it's getting too many outside things inside that labeled rectangle, I'll pause and readjust. And we will continue this process for all 3 cone sleeve images until we've completely annotated or labeled everything within the video. Now that we've labeled every frame of our video, we're going to export the labeling data and the video as individual images instead of a video. So to do so, we're going to click the menu button over here on the left and go to Export Job Dataset. Under this menu, we're going to select the export format. The format we need for our TensorFlow Lite model maker is the Open Images v6 1.0. And we don't just want to export the annotations, but we also want to save the video as images, because TensorFlow is going to be looking at the images with the labels. So when you've clicked Open Images v6 1.0 and saved images, we'll use the default settings and click OK. This process might take a little while, but it will notify you when it's ready to download. Now that you've downloaded that data set, you'll note that you have a zip file. Please extract that zip file or unzip it. You'll note inside of that new folder, you have 2 folders, one labeled Annotations and one labeled Images. Let's take a quick look at what is in these folders. So under Annotations, you'll note there are several files. The one we're really going to be working with has a name, Default Annotations BBox. So BBox stands for bounding box, and that represents the coordinates of the rectangle labels or annotations you created in CVAP. In the Images folder, we have a subfolder called Default that then contains every frame of your video as a PNG file. Let's set up our project. So we're going to be using Google Drive to store our project files. So let's create a project folder in our Google Drive. Now, instead of going to Google Drive and making that folder ourselves, our Colab Notebook is going to do that for us and make sure that we have the space to do so. So before doing this, please make sure you have at least a gigabyte of storage left in your Google Drive. If you're using your LAUSD account, you'll note that you have unlimited space, so this should not be an issue. Please give a name to your project folder in your Google Drive. You could just leave the default TensorFlow, works perfectly fine. And if you're interested, feel free to show the code behind connecting to your Google Drive account and creating that folder. So now we're going to press play. You'll get a pop-up that asks if it's okay for this notebook to access your Google Drive files. We're going to click Connect to Google Drive. It may also ask you to verify your login, so I'm just going to re-sign in to my Google account. It's going to then inform you of all the things this notebook will have access to, including editing, creating, and deleting all the files in your Google Drive. Just click Allow. This project is not set up to delete any files, although it has access to it. There is not a single line of code that's going to be deleting files, just creating them and accessing and reading them. So as soon as we authorize that, you'll note that we get a green check mark again, and it tells us that it has what's known as mounted our drive, and it gives us this path or location that it's been mounted. If at any point you want to see the files being used in this current project, all you need to do is click this little folder button on the left-hand side of your Colab Notebook called Files. And you'll note that we have a folder called Drive, and in there we have My Drive, and this will contain all the folders and files within your Google Drive. If you do anything with them here in the notebook, it will affect what's in your Google Drive. There's not actually a need to open this or manipulate them in this way, but if you'd like to see what's going on behind the scenes, feel free. We are going to upload our unzipped data set and then upload that to Google Drive. So when we upload that to Google Drive, make sure you go to your TensorFlow or whatever you named your projects folder and upload the annotations and images folders here. So you should see a folder structure as follows. You should have your drive, your projects folder. My name is TensorFlow. The annotations folder you've just uploaded, and the images, default, and image files folders, like so. Once those are in your Google Drive, we actually need to convert them and downsize them. So the images, depending on the camera and frame rate you used, are very large images that are not compressed very much. So we need to convert them from PNGs to JPEGs and downsize them a bit. You can run this code here, but if you want to adjust the downsizing, feel free to show the code and change this new size variable. I'm going to be downsizing these images to 240 by 240 pixels. It is perfectly okay if they don't keep their aspect ratio. That will not matter. This process may take several minutes to complete. Now that we're done converting our PNGs to JPEGs, we're going to convert our CSV file that we saw earlier into a more specific format that the TensorFlow Lite model maker can use. This code is going to convert your bounding box annotations to a spreadsheet that TensorFlow can read. You'll know that this code will also randomly split your data into 3 different parts. One part will take up 80% of your images and use that for training data. Another 10% will be used for validation data, and the last 10% will be used as a test set. Note that you may get an error when you run this code. Note that you'll still get the nice green check mark and the time it took to run this code on the side. If you want more information about dataset format explanations, feel free to read this optional explanation. Now we need to install the required packages or collections of software that include the TF Lite model maker package. So we're going to install all the software we need to make this model. You'll note if you read here, we need some very specific versions of TensorFlow. And we'll click play. And you'll note below the code will be an output of what the code is doing. So in this case, we're installing a bunch of software onto a Google server. And it's showing how it's downloading it, it's unpacking some zip files, and setting that software up. During this process, you may also note that you will get some red text in error. As long as this code is still running, these errors can mostly be ignored. There might be some compatibility issues that it talks about. You'll note that that is actually being dealt with immediately as it's installing a specific version of TensorFlow and then immediately installing a correct version of TensorFlow that will properly work with our tutorial today. You'll note when the code is done running successfully, you should see a green check mark along with the runtime underneath it, right near that play button as you scroll. So we can see that it took about 1 minute to successfully execute this code and install all the required software we need. Next, now that we've installed that software, here is some Python code that's going to import that installed software and basically set everything up that we need to run our TensorFlow model maker. So we're going to run this code as well. Again, this took about 6 seconds to run. We see a nice green check mark. All right, now we're set up software-wise. Now we're going to go to the step that trains our object detection model. This will take 6 different steps. In step 1, we're going to choose our object detection model architecture. In this tutorial, we're going to be using an architecture known as the Efficient Det Lite 0 model. There are 5 of these models, from 0 to 4, all with different average precisions, latency, and sizes of your model. Creating a machine learning model from scratch is a very long process that can be very difficult to do. And the TF Lite Model Maker software allows you to build on top of previously made models to reduce the amount of time it takes to make a new one. So we're going to be building on top of the Efficient Det Lite 0 model. Feel free to change this model based on the statistics you see in this table. If you want to change it, please make sure you change the model name from Lite 0 all the way to Lite 4, and this URI to say Lite 0 all the way to 4, and make sure that those match the architecture or model you'd like to build on top of. Lite 0 should be perfectly okay for this task. To set that model, click the play button to run this code. Now that we have our model we're going to build on top of, we're going to load our data set in. Reminder that our conversion earlier separated our data into 3 parts. 80% for training images. These images are going to be used to train the object detection model to recognize your cone sleeve images. 10% are used for validation. These images are what the model hasn't seen during the training process, but we'll use them to decide when it should stop training to avoid something called overfitting. Please read more following this link. And the last 10% are test images that we'll use after creating the model to evaluate the model's performance and accuracy. So pressing this code button will separate those 3 sets of data. In step 3, we're actually going to train our TensorFlow model with the training data. You'll note that we have many options during this training, and I'm just going to briefly describe some of the parts of it. Epochs equals 50 means that the training will go through the data set 50 times. Batch size equals 8 means that each step through the training process will look at 8 images at a time. So if we click this run button, we will begin training our model. This is the longest part of this tutorial. As the training commences, you'll note many statistics as it goes through each epoch or time through the dataset. As your data continues to be processed and trained, you'll note that the statistics, specifically the debt loss statistic, should be gradually going down. It might fluctuate slightly upward, but in general, the trend should be down. You'll note from the first epoch to the second, there was a great decrease, and it slowly decreases from there. This essentially tells you that your model is getting more and more accurate from training to training. Now our model has been completely trained. With a video that was annotated about 20 seconds long at 600 frames, it took about 13 minutes to train. We're now going to go to step 4 and evaluate the model with the test data. When we run this code, we're going to get a set of evaluation metrics that you can read more about following the link labeled COCO. The metrics to look at the most are the bottom ones where it says AP, and then it will say the name of the labels you gave earlier. I labeled them image 1, 2, and 3. And you'll get a percentage in decimal format of the approximate accuracy of your model. Step 5, export. The first part of exporting will be to export the TF Lite model file and the label file. Your TF Lite model file is going to be loaded into your project's Google Drive folder. Exporting will also apply the default post-training quantization technique known as full integer quantization. You could read more about quantization following this link, but what it will essentially do is take all the decimal numbers involved in your machine learning model and round them to the nearest integer. This will decrease the accuracy of your model slightly, but will increase the performance and runtime of object detection on your Rev Control Hub. Once your model is successfully exported, in your Google Drive folder for this project, you'll note that you should have the model.tflite file. In the next part of our exporting, we need to add what's known as metadata to the TensorFlow Lite model. Metadata are written descriptions of our file. So the metadata that we're going to add to our file consists of both human readable parts, which can convey the best practice when using this model, and more importantly, the machine readable parts that are going to be used by your robot to know how to use your model properly. So to do this, we'll need to click on two different sections of code. One will import some more pieces of software that will allow us to write that metadata to our file. And the next part of code will actually write the proper metadata to that TF Lite model file. You'll note that in your output for this code, it will show you that metadata and what is added on to your file. You'll note that it will have descriptions, names, and talk about the output properties of your model. You'll also see in your Google Drive that you now have a model_metadata.tflite file. In step 6, we're going to evaluate our TensorFlow Lite model. We're going to evaluate our model that we trained against our new model metadata file and see the difference between how it originally was evaluated and how it evaluates now that we've exported and quantized that model. You'll note that these will use the exact same evaluation criteria as we saw earlier. Once it's done evaluating your exported model, you can compare these statistics with that of your original model before export. So you'll note for each of our images, we were at about 75 to 80% accuracy for each of those. After exporting and quantization, where we turned everything into integers, we have reduced the accuracy a bit, but you'll note that we're over 70% for recognizing each of these models. And we can test our model against other images now that we have everything complete. So to do so, we're going to run this set of code. We'll just set up our testing environment to load other images and to evaluate them against our specific model. And then we can run that object detection and show the detection results. So for this to work, you actually need a URL of a test image. So I have taken an image and uploaded it to a website. There's many websites that can do this, like postimages.org, where you can upload an image and get a URL of that image as well. So I have a test photo here that I've already uploaded. And we could set what's known as a detection threshold. So it will only tell us if it detects this object with a certain percentage of confidence. So based on my evaluation, I'm not sure if I want to see if it has a 75% confidence. That's a fairly good confidence, but maybe a 70% confidence, still pretty good confidence in what it's detecting. So we're going to run this. It might take a minute to load, but when it is done, you'll note that it's going to show us a visual of what it has detected. Oh, look at that. Wonderful. So here's my test image. And in the evaluation of it, it has determined with 96% accuracy that it's looking at image 3, which is my third image on the cone sleeve. This is very good. I suggest that you take several of these images and test this out before loading any of this onto our Rev Control Hub to make sure that your model is working as accurate as you want it to. I also suggest that your test images here are, again, in your field, in a place and position that your robot will actually be seeing these custom sleeves in an actual match. Now that we have our TensorFlow Lite model, we're going to prepare it to be used on our Rev Control Hub. So because the TensorFlow Lite Model Maker is a newer technology, the stock robot controller app that runs on your Rev Control Hub will not properly load the new TF Lite model file that we have created. So we're going to need to update that app. So you'll need to download that, what's known as an APK or Android package. So to download the updated robot controller app, please click the link here. Once that app is downloaded, to update your Rev Control Hub, you'll need to connect to the Rev Control Hub's Wi-Fi and click on the Manage button. If you scroll down, you'll note there's a section that says Update Robot Controller App. From there, you'll click Select App and select the APK file that you just downloaded. It's important that you click through all the warnings and dialogues to install the new robot controller app. And you'll note that you'll also need the latest version of the FTC Driver Station app on your Rev Driver Hub as well. But this can be updated on the Rev Driver Hub itself by connecting it to Wi-Fi and running its Software Manager app in order to update it. The Rev Driver Hub application is not specially updated for this, but will work with it anyway. Now we'll need to download your model. So where is your model anyway? So you can go find it in your Google Drive folder for this project, or if you forgot where that is and you run this piece of code, it will tell you where in your drive that file is located. So it says that mine is located in my drive in the TensorFlow folder, which I have open here. What you'll want to do is download the file labeled model_metadata.tflite. This is the file that is your model and has the metadata that will allow your robot to properly read the file. So if you right-click on the file and click Download, you'll download the file to your computer. Once you've downloaded your model, it's time to load it onto the Rev Control Hub. Again, you'll connect to your Rev Control Hub's Wi-Fi and click the Manage button. When you scroll down, you'll note that there is a link titled Manage TensorFlow Lite Models. From here, you can upload your model by selecting the model_metadata TF Lite file that you just downloaded. It's important that you do not use the model.tflite file, as it may cause errors since it doesn't contain proper metadata for your robot to read the file properly. So let's go through what that looks like. Now that we've connected to our Rev Control Hub, we're going to click the Manage button. Then we're going to scroll down and find the section that says Manage TensorFlow Lite Models, and we'll click the link. This will open up our upload page. We'll click the button that says Upload Models. From here, we just need to select the model underscore metadata.tflite file we downloaded previously. Once your model has been uploaded successfully, you'll see it in this list. Again, it needs to be the model underscore metadata.tflite file. Now that you've successfully uploaded your model to your Rev Control Hub, all that's left is to code. There are some great tutorials on FTC docs about using the on-bot Java programming or the blocks programming to use your TF-Lite model. Please make sure to read up on those to see how it works. And with that, if you have any questions, please leave them in the comments below and I'll try to answer as many as I can. Thank you.